Alright. So, classical field theory we will do it today. So, examples, let us look at some examples to keep what we are going to discuss in this. Waves on a string, okay. So, height, but we will assume right now that it is a small amplitude wave. So, that is what we will assume. A Navier-Stokes equation, it is a nonlinear, but we will do it later. A 5-4 theory, which I am going to tell you what is 5-4 theory. Schrodinger equation, which all of you know. Classical thing, inclined Gordon equation. So, these are some examples, some of it we will do in detail, some will do it not in so much detail. Well, the other, okay. So, we will do that. So, so let us look at example. Basically, let us think of string first. So, field is I am denoting by phi, and phi is function of x and t. So, earlier particle has position and velocity, okay. So, there are two coordinates for particles, but here there is a field which has a value for given x and given time, right. A string is an example, or temperature in this room, that is an example. Velocity of particles, velocity of in this room, not particle, velocity in this room is an example. So, let us take example of string. So, I will not derive in detail, but we will motivate it. So, kinetic energy, how do I define? For particle is half mv squared, right. Mass is a mass of the particle. Normally think of point particle or a sphere, but a string is a extended object. So, we define, basically we are going to use the same formula, half mv squared, but m will be the kind of, we need to think of total mass, but v will be different at different places. So, we have to just say density. So, if this is a string, then we think of small element here, so rho dx, and then velocity of that element, which is d phi by dt, is moving all in transverse direction, okay. There is no motion in that direction, so it does transverse direction. So, d phi by dt is the vis velocity. So, this is a local kinetic energy or kinetic energy density multiplied by dx, well this half is convention, okay. So, this is a kinetic energy which is function of phi and density. Similarly, we can define potential energy. So, potential energy is coming from the curvature, right. A string, when it is undulated like that, it has a undulation, okay. So, this is the potential energy, this multiplied by elastic constant kappa, okay. So, that is the potential energy of the string. So, we have 2D energy and total energy will be T plus V, but Lagrangian is defined in a similar way, is T minus V, right. So, Lagrangian it is the same thing, kinetic energy minus potential energy, but instead of particle we have for field. So, this is T minus V d, okay. Now, action will be, so Lagrangian will be integral T minus, sorry T minus V, which is total energy minus potential energy. Now, that will be integral dx and this object rho phi dot square minus and da 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 da. So, what is action? Action is L dt. So, this is what I wrote, action, okay. Now, please keep in mind that for particle we define the initial condition and final condition, right. Now, here initial condition will be initial condition of the string, it could be starting like this with certain velocity, okay. So, phi is 0, but it has velocity is a starting point, or it could be like that is the initial condition, and final condition is somewhere it goes to. So, this is we have to phi x t equal to 0, this is initial condition, and phi x t equal to t final is a final condition. So, in Lagrange, in action principle we define both initial condition and final condition, okay, and then we see what is the evolution from initial to final and what is the equation of motion, that is what we do it. So, we can do similar analysis for fields, alright. So, we need to give initial condition and final condition, these are the constraint, right. I mean, I am not making anything telling anything mysterious. For particle we have initial condition and final condition, and in between particle follow the classical path. Okay. Now, if you see here we have dt and so that is dt. Now, t and v are function of x, we integrated, right, t is integral dx. So, you see that dt dx will come. For particle we only have integral dt, but here we have dt dx and some function of phi partial with x, a partial of phi with x, d phi by dx and d phi by dt. Okay. So, these are the three independent variables, phi, partial x phi, partial t phi. Okay. So, this is called Lagrangian density, Lagrangian density. Okay. So, if I integrate Lagrangian density with dx, then I get the total Lagrangian, and I integrate that with time, then I get action. So, here for this system is like string, this is the Lagrangian density, this is not the total Lagrangian, but this is function of x, well this function of phi, this one and this, it could be function of xt as well, but normally we will have function of phi and this. Okay. Now, I am quickly going to derive principle of least action, well equation of motion using principle of least action. So, for particles we have principle of least action, which is the particle follows a trajectory for which action is minimal or extremum, actually not minimal, extremum. So, here also L dt is extremum. So, we want this object to be extremum given initial condition 0 to final. Okay. Now, of course, this function is reasonably complicated. So, I need to make, now is that clear? That is a principle of least action, and that is applicable for fields as well, all sorts of fields. This is a general theory like Euler-Lagrange equation for particle, similar thing we are going to derive for fields. So, I want to make delta s by delta phi to be 0. This is as I said, is a variation calculus, it is not d by dt or. So, if you recall how I was varying the field, so let me just show you that part. So, if you recall what we did, so I am going to write this dt dx as dx mu. Okay. So, in 1D it is going to be dt multiplied by dx, and in 3 dimensional fields, okay, then we have dt d dx dy dz, this is our dx mu, basically inspired by relativity. This is space time, okay, this is space time, okay, but in 1D it is just dt dx. I am not going to do relativity right now, well in between we will make some connection, but we will basically stick to non-relativistic fields. Okay. So, this is dx mu, right now you just think of it as dt dx. Now, how do I get this delta s? So, I said phi, you vary the phi by a delta function, right. Remember we had done this thing. So, I am varying this phi by epsilon delta x minus x prime. So, we said there is a field and you just give it a small kink at x prime and integrate with dx. So, I am going to basically get something as function of x prime and then do division by epsilon and take that stuff. Okay. So, this is the integral with dx. So, Lagrangian, which is function of these, okay, phi which is perturbed phi, and then subtract this with Lagrangian with original phi and its derivatives. Okay. When I subtract off, I need to do the expansion of this, right, Taylor expansion, because we will assume these two quantities to be small. Okay. Following exactly the same procedure like what we did for particles, we get this. Okay. So, first this term minus this term will give you that one, okay, because basically you will get contribution from here, and the second one will get contribution like this. So, I had to take a derivative with relative to this and then multiply by that, but now I have partial derivative of delta function, and delta function I do not know to deal with it. You recall any function delta x minus x prime fx prime dx prime is fx, sorry what I am saying, delta, right. So, I want without delta function without derivative. So, what do I do here? I use parts by parts. So, by parts if I do it, then derivative will come here and delta will be outside, and that is the reason, and we get a minus sign, right, there will be minus sign. So, that is why the minus sign, and we get this under the assumption what, there will be another term called surface term, right, the surface term. No, I mean when I do the derivative by parts, I will get a surface term which will be delta L delta mu phi and delta function, first function integral of second. So, this is a surface term which is at 0 and T final minus this term, the one which is the next term minus this term, okay, integral with integral, okay, the integral, but this term is 0 surface term because at delta function is 0 at beginning and at the end. So, we get this, and I want the action to be extremal. So, I get 0, and this is Euler-Lagrange equation. This is Euler-Lagrange equation. Okay. It is very similar to what we do for particles, right. For particle, what do I write? D by dt, no sorry, partial L delta x equal to d by dt of delta L by delta x dot, right, that is what we write. So, instead of x I have to say phi, right, this x is replaced by phi, and d by dt is replaced by these derivatives, but there are 4 derivatives in 3D, and in 1D, well, one time in one space there will be 2 derivatives. So, let me write this so this is, there will be 2 derivatives. So, let us write that. One will be d by dx delta Lagrangian density del x phi, and there will be other one which is d by dt, the minus sign, time derivative. Now, I take Lagrangian density del of del t phi. Remember, Lagrangian density is function of phi, d phi by dx and d phi by dt. So, I need to have both these 2 terms. So, here there was only one independent variable time, but here I have 2 independent, well 2 basically very independent variables for phi. So, I need to do this x and t. Okay. So, if you know this well, then you can also write down for fields, and you need to know this equation. Okay. In field theory, we need to know this equation. These were classical fields and quantum fields. So, we need this, we need to derive equations from given Lagrangian. Okay. Is that clear to everyone? So, I want to emphasize on this, that we need this put to 0. So, now let us apply this for string. I know the Lagrangian, so I should be able to derive the equation. Okay. So, this is what I had written in the last slide, right. So, this for 1D non-relativistic. Relativistic has only some minor changes, you need to keep a covariant, contravariant, that combination, but let us not think about that right now. So, my Lagrangian was this, right, for a string. So, this is function of this d phi dt, and this is d phi dx squared. So, when I substitute, what will I get? What is partial L partial phi? 0, right. This is not function of phi. Okay. So, partial L partial phi is 0. What is partial L partial? dx phi, this term. I look at it here, this is the term, right. d phi dx is the function. So, when I take derivative, what will I get? Half kappa and derivative of this with that. So, it is going to be 2 dx phi. Okay. So, 2 and half will cancel. So, kappa d phi dx. Similarly, what is this one? dt phi is just for, this is a minus sign, I am sorry, this is a minus sign here, there is a minus sign here, right. There is a L has a, this is a minus sign, there is a minus sign here. So, I will get that dl partial L partial of d phi dt. So, this will act on that, I will get rho dt phi. Substitute it here, I get first term will give us, there is a minus sign out there. So, minus becomes plus. So, that becomes plus kappa. I had to take a derivative, kappa is constant. So, I take a derivative with x. So, I will get dx phi, double derivative of phi with x. Second term minus and derivative of this with t. Rho is constant, density is constant, we will assume that rho dt phi is 0. Okay. This means double derivative in time. So, this is the equation of motion for a string. Okay. That is the equation. Okay. And of course, we know the solution, it is sin kx minus omega t and like that.